Okay, so the Benford's Law project actually connects very well to topic number 5, Poisson behavior in Fourier analysis. It connects a little bit to the 3x plus 1 problem. And so the natural question is, if I give you a sequence of numbers, what can you say about the distribution of leading digits? So imagine you write down the first trillion Fibonacci numbers, and you tabulate how often you see a first digit of 1, a first digit of 2, a first digit of 3. I don't want the correct answer. I want naively, what would you conjecture as to how often the first digit is 1? 10%. 10%. Good. So the most natural thing is all the digits are equally likely. And then you realize you had a brain freeze, and 10% is wrong. So what do you fix your conjecture to? 11%, because 0 never occurs as the first digit. The actual answer is 30%. 30% of all the Fibonacci numbers have a first digit of 1. And the proof of this, actually, we might even be able to do the proof of this in the introduction. So, let's say you have a sequence of numbers xn, and let's let yn equal the log of xn base 10 mod 1. Why is this a good thing to do? Well, let's say I can write xn as its mantissa times 10 to a power. If I want to study the first digits, I don't care about the 10 to the power. I only care about the mantissa. And so if I take the log of xn mod 1, I'll get the log of the mantissa, and then I'll get a plus k mod 1. Well, any integer mod 1 is just 0, so I can actually drop the plus k. And so what's nice about this is you can begin to see, oh yes, Fourier analysis is definitely going to be useful here. I have the mod 1 function again. That's one of the things I want you to get out of this course is, for certain types of problems, you should have a Pavlovian response of, let me use this. So understanding the distribution of the digits of xn is the same as understanding the distribution of the log of the mantissa mod 1. And the mod 1 is harmless. So let's say my xn's live here. These will be my mantissas. And down here, these will be the log of the mantissas. So all the mantissas go from 1 to 10. The log, okay. When I exponentiate, 10 to the 0 is 1, 10 to the 1 is 10. How do I have a first digit of 1? Well, what number exponentiates to 2? So it'll be the log base 10 of 2, which is about 0.3. So all these numbers exponentiate to a first digit of 1. So what typically happens is the logarithm of your sequence is uniformly distributed. And if the logarithm is uniformly distributed, then when you exponentiate, you'll have this digit bias. So really, what Benford's law is saying is, put on these special glasses that automatically take the logarithm, base 10, and throw away the integer part. And then you'll see the uniform distribution. As most people are not willing to do that, we end up having what we call Benford's law. I'm actually editing the first book on the subject right now, so if anybody's interested, there's also opportunities for stuff like that as well. So the questions become, which data sets satisfy Benford's law? The IRS cares about this because a lot of tax returns by big corporations do. And so nowadays, when a corporation submits their tax returns, the accountants do quick Benford law tests. And if the numbers look suspicious, they ask the companies, are you sure there wasn't an error in the file you sent us? Because they know if the IRS is able to, they will conduct tests like this. So let me prove to you, using section 5, that the Fibonacci numbers satisfy Benford's law. So what we're going to show is the Fibonacci satisfy Benford's law. So the Fibonacci's is fn plus 1 is fn plus fn minus 1. If you guess fn equals r to the n, this is how you solve difference equations like this. You'll see that r basically has to be related to the golden mean, and eventually you get Benet's formula, which says fn is basically 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. My index of n might be off by 1 depending on how you count the Fibonacci's. I don't quite remember. So you can quickly prove that this is a formula for the Fibonacci's. To me, this formula is always amazing. The Fibonacci's are integers. I have square roots, I have division by 2. It always comes out to be an integer. Now, when n is large, this number is less than 1 in absolute value, so this number becomes insignificant. So the nth Fibonacci number is essentially this. And then this is where you just do some small amount of bookkeeping. So the log base 10 of the Fibonacci number is going to be approximately n times the log base 10 of 1 plus root 5 over 2 plus the log base 10 of 1 over root 5. Well, this is just a fixed number. It's just going to shift everything. If this is uniformly distributed, if this is equidistributed, so will it be when I add this. There's your number alpha. Alpha is irrational. And alpha mod 1 is equidistributed. Fibonacci numbers satisfy Benford's law. You can then start to ask, how quickly do they satisfy Benford's law? One of my favorite examples is look at powers of 2. Because the log of 2 base 10 is irrational, these will be Benford. But there's an issue. How many megabytes are there in a gigabyte? I'm sorry? 1024. 2 to the 10th is 1024, is approximately 1,000, which is 10 cubed. So in terms of the first digit, it's almost periodic with period 10. It's a long time before you get the first power of 2 that starts with a 9. And so one of the big things the IRS and other people care about is how rapidly does Benford behavior set in? How many data points do I need? There's lots of wonderful topics like this. These make excellent projects, thesis projects, etc., etc. Okay, so the main result I have in the subject is a lot of products of random variables are Benford. The 3x plus 1 problem is Benford. Let me just briefly mention why products of random variables are Benford. So this requires a little bit of probability, but the main idea is a lot of physical quantities are the results of multiplication of various quantities. So let's say I have x is x1 times x2 times xn, and I want to understand the distribution of digits. Well, the log of x then is the sum of the log of the xi's. And I can just write that as the sum of, say, yi, where y is the log. I now have sums of, say, independent random variables. This becomes normally distributed. And it'll have increasing variance. But I only care about this sum mod 1. And if you look at a normal distribution with increasing variance mod 1, it actually collapses to the uniform distribution. So this is a quick way to see why so many processes satisfy Benford's law. Because so many things can be written as products. I have a paper with Alex Kontorovich where we look at the leading digits of the 3x plus 1 iterates. And we see Benford behavior there. And one of the key ingredients is how well can you approximate irrational numbers by rational numbers. We need a quantified version of equidistribution. And so the stuff we were talking earlier about continued fractions would come into play there.